Welcome to Web Handling. My name is Dave Roysum. I am super excited to continue our new series on equations that changed web handling forever. In this show, we explore how the simple traction equation shows us how to design the wrap angles on driven and idler rollers alike, as well as troubleshoot certain web handling issues. The motivation is simple. Just as your life depends on the tractions of your tires against the road, your business depends on the traction of your web against rollers. No worries, kiddos. I'm going to make this as painless as possible. The traction equation has a royal pedigree. More than 200 years ago, people were using it to size a certain type of brake, the band brake, as well as belts, pulleys, and other mechanical components. Thus, its many names. So, it's clear that the web handlers didn't invent the equation. They stole it. No, that's too harsh. Borrowed it isn't right either, because we aren't going to give it back. Rather, we co-opted it. By that, I mean we adopted it for our own use. So, what are those uses? By far, the most common is to size the minimum required wrap angle for idler rollers and driven rollers alike. Web handlers treat these the same because both bearing drag and motor torque are just numbers with signs. The equation can handle either or both with equal ease. Web handlers also use the traction equation to troubleshoot certain product process design issues such as slippage, drive control, and the possible need for traction enhancements. The tension ratio is the high tension side divided by the low tension side, no matter which side of the rollers those are. We might call the ratio the traction capacity. It really is a measure of how much work we can do on the web or the roller. The less than symbol tells us that the maximum tension ratio that can be sustained without sliding. E is the base of the natural logarithms. Because of that exponent, traction capacity is supersensitive to even tiny changes in mu or theta, where mu is the effective coefficient of friction between the web and the roller, and theta is the wrap angle in radians. Let's take a simple everyday example. The COF between many webs and a metal roller, where the air entrainment is negligible, may be around 0.3. Let the wrap angle be 90 degrees, which is 1.57 radians. If you do this simple calculation, the tension rise has to be less than 60%, because attempting anything more will cause the web and roller to lose traction and thus slide. Knowing that we don't want to be anywhere near failure, we may choose a safety factor of 2 on the traction ratio rather than mu or theta. Thus, a 30% tension rise is the maximum safe amount. Thus, if you enter with a tension of 10, then the exiting tension better be less than 13. Of course, you could enter with 13 and leave with 10 because the equation is symmetric. Rubber covers are mostly used for nip rollers. However, there are occasions where a designer might choose a rubber cover solely for the purpose of improving traction over a plain metal surface. The COF of many webs against rubber might be on the order of 1. If we compare rubber with metal for the same 90-degree wrap angle, we find that rubber can sustain 140% tension rise. In other words, increasing the COF or wrap angle by a little more than 3 can increase the amount of extra pull the drive roller can impart by almost 5 times. That is the power of exponents. The band break also tells us something quite interesting for the case where tension is quite low on one side of the roller, such as during threading. We will rearrange the formula to solve for the high tension. If T low is near zero, T high will also be near zero. Thus, in practice, the drive roller just spins. On another note that might surprise you because it defies intuition is that traction is not, I repeat, not affected by wrap angle, except for in the very rare and odd cases of non-Coulomb behavior, such as adhesive and vacuum rollers and a few other situations. At this point, you should be asking how to measure COF. It turns out that you use the same band break equation with the simple setup described in Chapter 4 of the Web Handling Handbook to back calculate that parameter. Of course, there can be traction complications that defy this simple equations. These complications include air entrainment and vacuum rollers, which are covered in Chapter 4, but also with adhesion, which is poorly understood and documented. Fortunately, adhesion is rare, so we rarely need to consider it. Please note, as simple as this equation is, you may want to just use the free Abbott app below for two reasons. The first is that math's already done and double check for you. The second is the app can also do traction in the presence of air entrainment. I hope you've been inspired by the elegant simplicity of the traction equation and how to use it for everyday design and troubleshooting. Stay tuned for next week's show where we will take a deep dive into air entrainment. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. See you next time.